start today's session. There will be 2 workshops today by PhD students and postdocs here at the university. We can start our session at 2:15 in the afternoon. There will be the second part of this workshop, and you, François, you will also have 15 minutes if you want to complete part of your seminar of yesterday, or if you want to intervene in some topics that are presented today in the workshop. So we can start, and the first speaker is Schuster, who is postdoc here at the chair. So please.
So thank you, Julia. I hope everyone could hear me. Thank you for this introduction. Yeah, I'm a postdoc now for quite a few years here in Erlangen, and my talk today will be about the Turnpike phenomenon for optimal control problems under uncertainty. So this is ongoing work, so recent results and current work together with a colleague from Nationale University in Nagoya called Professor Sakamoto. So I first want to start with a short introduction about the Turnpike phenomenon. Maybe not everyone is aware what exactly is the Turnpike phenomenon. And this came up in economics in 1958, so more than 50 years ago. Basically, there is a highway in Florida in the United States called the Turnpike Highway. It's a connection between Miami and Orlando, city of Orlando. And the idea is that when you are close to the highway, when you're living close to the highway and you want to travel between the 2 destinations, it will always pay off to really use the highway. But if you're far away from the highway, then maybe there will be a faster way which don't touch the highway. So maybe if you're living here somewhere close to the seaside, then maybe you will not use the blue turnpike. But if you're living somewhere close to the turnpike and your destination is somewhere close to the turnpike, then it will always pay off to use the turnpike. And when we translate this to mathematics, basically to control theory, for example, that means if we consider some dynamical system, some time-dependent optimal control or a control problem, then there will always be a connection to some corresponding turnpike, to some steady state, in the sense that if you consider a long time horizon, then the dynamic, so the time-dependent optimal control, will be close to the steady state control or to the corresponding turnpike for quite a long time. And this is what we're going to analyze in the next maybe 15 to 20 minutes. So as a motivation, we consider an optimal control problem with time-varying feedback control given by some objective, by some integral objective, depending on the control and depending on the state. We consider, let's say, a simple linear transport equation with some initial condition and some boundary feedback control, in the sense that the control given at the beginning of the space interval depends on the state at the end of the space interval. You can imagine, for example, a possible application is traffic, so transport of vehicles on a street. Maybe you will want to control the traffic light at the beginning of the street, but this should depend on the amount of cars in the middle or at the end of the street. Or, for example, another application would be the distribution of some pollutants in a water channel or water pipeline. There you want to think about, okay, what do I need to insert in the pipe in the beginning to guarantee that the pollution in the end is not so high by measuring the current state of the pollution in the end. So this is maybe a motivation why we consider this kind of transport equation with the time-varying feedback control. And if we start very simple, just doing some simulation without doing mathematical analysis, the first thing we observe is that, so the application here was we just multiply the control with the final state, so there is no G around, there's just a multiplication. Then we exactly see this kind of turnpike behavior in the sense that we start from some initial state, then the control is quite active, trying to steer the optimal state to the turnpike, which is the red line in the background. Then we stay at the turnpike for quite a long time, and in the very end we leave the turnpike to reach the, let's say, final destination. In case of the transport equation here, the final destination is not really a final destination. This bump or the sink in the end is just because when we start the control, let's say here, or later than here, then the control won't reach the end. So in the optimal control problem, the control in the end is actually 0 because it will just not reach the end of the interval. So and then a very important question for us is, what if the system is not deterministic? What if some uncertainty appears in the system? I mean, many applications are modeled as deterministic systems, but actually there is a lot of uncertainty in the system by parameters are not clear. As I said, for example, in the water pipeline networks where we consider the pollution, it's not a priori clear where exactly we should measure to get the optimum measuring results. Maybe the sensors are not placed well. Also for the traffic lights, maybe there is just some bigger cars, some smaller cars, so there's a lot of uncertainty in the system. Please, yes? Yes, in this case, it was basic quadratic control and stayed close to some reference state in the L2 norm, yes. Yeah, sorry for not mentioning that. So yeah, to the uncertainty. So where do we add uncertainty in the system? I mean, for us, one big point is the source term on the right-hand side. So maybe we do not exactly know the behavior because maybe we just don't know about the inside of the pipe, about the roughness of the pipe or something. And the second point is the initial state. So maybe we can get an idea how the initial state is in our system, but we don't know it exactly everywhere. So this is where we insert uncertainty in the system, which means on the right-hand side of the transport equation, we replace the constant m just by a random number. The initial state is replaced by a time-dependent uncertainty, or by space-dependent uncertainty in this case, modeled by Fourier series, by randomized Fourier series. And then we replace the state in the objective and in the feedback control by the expected state. So to say we want to control the expected state to some desired state in the end, and we also the control will react on what is expected to happen in the end of the space interval. And also for this case, so here is a picture of the random boundary data. So when the blue line is the deterministic initial data, when the blue line is the deterministic initial data, the randomized Fourier series really guarantees some real uncertainty, not just a random number. So it might happen that we get a different behavior using these randomized Fourier series. But we will come to that later in detail, why we choose this way of modeling uncertainty for the space dependence. Also for this part, we do some just basic simulations without doing analysis first, and we observe more or less the same behavior. So the control in the beginning, I mean the control obviously is deterministic, but the corresponding state is random. So we observe again some control action until the control reaches some turnpike, so some constant feedback control it is in this case, and the corresponding state also reaches some, or the blue line is the expected state here, also reaches some turnpike after short time and will be close to the turnpike for almost the rest of the time interval. And now the questions we ask ourselves is, so first, how can we prove a turnpike result in this setting? And the second is, what is with the uncertainty? Can we get some expression of how these different scenarios are close to the expected state, are far away from the expected state, and also from the turnpike? And this is what we're gonna analyze, or what we started analyzing and are currently doing for different systems. So first, we start with a simplified version of this. So we start with a transport equation with just a boundary control without the feedback, just to get an idea of the analysis, how we can prove a turnpike here. So we consider is the transport equation together with some initial state, and here no feedback boundary, but just some boundary control. So let's just control our system without looking forward what will happen at the end of the space interval. And here we splitted the objective function because from the theory, we need different assumptions on the control term and on the corresponding penalty term for the states for the transport equation. And we consider the corresponding steady state optimal control problem, which will give us the steady state control, which is the turnpike in this example. So yes, we need two assumptions. So the functions in the objective function, f and g, are supposed to be convex. a very basic assumption in control theory or in optimization in general. And in the first condition, we need some minimal growth for the control. So that means the function f, that is the cost of the control, should be, the cost should raise with some lower value. Having this condition, which is basically, if you translate it, a strong convexity assumption on the function f, and on the same way for the function g, we need some Lipschitz condition, which guarantees that the difference in the states is not growing infinity fast, so it's bounded by some Lipschitz assumption. And with these assumptions that are not so tough, or at least you see them quite a few times in optimization or in control theory, having some Lipschitz assumption or some strong convexity, strict convexity assumption, we really can get a Turnpike result of the following form. The optimal control problem, together with both assumptions, lead to a Turnpike inequality that is given by the L2 distance between the dynamic control and the corresponding steady state control is bounded by some constant c. So this is a classical, it's called integral Turnpike result. There might also be different Turnpike results, exponential Turnpike results, or measure interior point Turnpike results. But this result guarantees that if we consider an even longer time horizon, if we let go the t up to infinity, the distance is still bounded by some constants, so we get arbitrarily close to the steady state as it is shown in the picture, which is also another simulation of the Turnpike with just the boundary control without the feedback control. And just to give you an impression how we can prove these kind of Turnpike results given the assumptions we have, I want to shortly go through the proof, through the different steps we apply in the proof. And since our model is, let's say, more or less simple in this case, we have just a transport equation, not even a system of transport equations, we can state an explicit solution which simplifies the analysis enormously. I mean, don't get me wrong, it was still tough to figure out how this works, but at least we could exploit the whole explicit solution, which was very nice in this example. So the first part is just write down the explicit solution, insert in the objective function, and then we get some unconstrained optimal control problem. So the second step is, for the unconstrained optimal control problem, we need to compute the derivative in order to derive necessary optimality condition. So the Fréchet derivative can be computed by considering some control variation, like we consider a control u plus h, and then we use the convexity properties of the functions f and g, and then we get an expression for the Fréchet derivative of the objective. In the third step, by the strong convexity assumption, which allows us to apply direct method for calculus of variations to get the existence of some optimal controls in this linear control system. So we can consider, let u delta and u sigma be the optimal controls of the dynamic and corresponding steady state problem. Then we can write down the necessary optimality condition, which is basically the objective of the dynamical system is equal to 0. So the derivative of the objective of the dynamical system is equal to 0. The same for the steady state problem, equalize, and then we get here a distance between the f's in reference to a distance between the derivative of the g's. And then there is one slide of mathematics. I just wrote a few formulas because basically see the Turnpike already here without maybe knowing, but we start again from the strong convexity assumption. This just the very beginning of the formula, we just write down the convexity, the strong convexity assumption we had in the beginning. Then we apply the necessary optimality conditions. We use integration by substitution. We use integration by parts. We do some mathematics. And after a few steps, we see that this left-hand side, so the L2 distance between dynamic and steady state control just depends on one term that depends on the time interval t minus L over c and t. And the second term just depends on the integral from 0 to L over c, which is basically what we see as a Turnpike, because the constant just depends on a small interval in the very beginning and a small interval in the end. But the whole middle part from L over c to t minus L over c does not appear in the L2 distance. which is there we already see the turnpike. Then we do some more mathematics. We use Cauchy-Schwarz inequality, we use the Lipschitz assumption, and in the end we come to some quadratic formula in the L2 distance, and then we can just choose solver for quadratic equations. We find a solution smaller than 0, which is not possible for the squared L2 norm. We find a solution larger than 0, and which is the constant for our turnpike in this scenario. So basically we found some way how to prove a turnpike, at least for the deterministic result, for the deterministic optimal control problem with the boundary control without the feedback. So how can we get this to the next level? The next level is we start adding the uncertainty, but also first we just add the uncertainty in the initial data. So when talking about PDEs, regularity is a big problem. So when considering random initial data, we cannot just arbitrarily say, let's just choose any random data, because any random data might not have the right regularity properties to guarantee the existence of a solution. And this is why we chose this approach with the randomized Fourier series, because they guarantee us, at least almost surely, that we keep the regularity. Meaning that we start with deterministic initial data, which is the R ini here. That is, for example, in L2 in space. Then we define the Fourier coefficients, we define the basis functions, and then the Fourier series, for every term, we add some random number. And then there are some theorems, all based on the Paley-Sigmund theorem, also from, I don't know, 30 or 40 years ago, that guarantees us if the R ini is in L2, then the randomized R ini is almost surely in L2. So we keep the regularity properties, and we do not need to care about the existence of a solution of our PDE. This is why we choose the randomized Fourier series. And for implementation, I mean, you can simply cut the Fourier series after a few terms. So it's also quite nice to do some computations with. And then we get a similar result for the case with the random initial data, where we replace the state by the expected state in the end, which is, when we think about it, not so surprising, because since we don't consider some feedback here, the information given in the initial data will just vanish from the system after some time, namely after the beginning of the time interval. So after a short period of time, the system is deterministic, and then we can directly come back to the deterministic proof we had before. So, okay, meaning the uncertainty in the initial data, in this case, we can easily handle. So the maybe more interesting case is what happens if we add uncertainty in the boundary condition. So now we say the boundary data is just a random number, or multiplied by a random number, and we need two additional assumptions, defining some number E0, defining this term, and assuming that both terms are bounded, which is maybe from the first side a bit confusing, but this will basically guarantee that the expected value of the solution of the transport equation will exist. So that means, imagine we have some Gaussian distributed variable, then we have exponential term of z, and here in the density we have exponential of minus z square. Then this will be uniformly bounded, and the second term will just be bounded by, I think maybe not one, but by some constant. So this is just to guarantee that the expected value exists, which is true for, say, all the common probability distributions. Maybe you can construct some distribution that don't satisfy these properties, but usually this is true. And then we can get, again, a similar result. So just to mention, I already wrote C here, but this is not the same C's in every, not the same constant in every Turnpike inequality, but also for this case, with a random source term, we can get a similar Turnpike result. The control satisfies a Turnpike property, the corresponding expected state, and for all realization, for every scenario, when we consider a single realization of the boundary value of the random number m, then we have a deterministic scenario and the Turnpike property holds. So, okay, the next question for us was, can we get some information about how these scenarios differ from the expected state or from the Turnpike? sorry, I wanted to give a short, or I wanted to shortly note the difference in the proof. So we can, again, exploit the explicit solution of the transport equation. The only difference is that in our computation of the function j, of computing the derivative, is that we have to explicitly compute the expected value that appears in the objective function. And if we do some computation, we explicitly see here we have the integral over the E0, there we have the integral over the E1 that were defined before, and with the assumptions we made before, we just guarantee that these integrals exist, that the expected values exist. So this is the only difference in the proof. Apart from that, we can follow the proof from the deterministic scenario we had before. So we have the Turnpike result now for the optimal controls, which are deterministic. We have the Turnpike result for the corresponding expected values, but we have no information yet on, for example, some variance properties. Yeah, how does the variance behave in this setting? And to get an idea about the variance, we have to consider a stronger assumption, because the variance depends on the squared expected values and on the expected values of the squared states. So the strong convexity property we had before is simply not enough anymore. We have to assume like an even stronger growth condition on the function f, which is given by, I don't know, let's call it a squared convexity property assumption, where we have the squared of the x1 and the x2 on the right-hand side. So in the strong convexity property, the squared would vanish, but here we need to assume this. And with this assumption, we can get like a Turnpike property for the squared controls, so squared Turnpike property, so to say. And due to the expected value, we get a Turnpike property for the corresponding variances of the states, which is quite nice for us, because with this, we have basically like 3 convexity properties. That means if we just consider one realization of the random variable, we are in a deterministic setting, and we get the Turnpike. We get the convergence of the dynamic state to the steady state. The same holds for the expected value. We get the convergence of the expected value to the expected steady state. And in the last point, we get the convergence of the variance of the time-dependent scenario to the variance of the steady state scenarios, allowing us to have like a convergence in terms of probabilities, which means that we can use, for example, confidence intervals around the expected steady state to get an idea where the dynamic state will be if the time horizon goes to infinity. That means, due to the convergence of the variance we had, we say, in the 80% confidence interval of the expected steady state. So we just solve the steady state optimal control problem, and then we still get an idea what will happen to the dynamic scenarios if the time horizon goes to infinity, including all this uncertainty, which is, in my opinion, a quite nice property, since this allows us just to analyze the steady state problem and not the dynamic problem. Okay, so some extensions of this work we considered very briefly. If we add some space dependence here to the right-hand side and some term b of x here, we have the space variant transport equation control system, which gives us exactly the same Turnpike results. We can still exploit the explicit solution, we can still compute the derivative, and we can go through the steps and get the same Turnpike result. The situation slightly differs if we add some time dependence here, because it's not a priori clear if we add some time dependence here, what will be the corresponding steady state problem, because we cannot just remove the time dependence to get the steady state problem. And what we observed here is that the corresponding Turnpike is now not some steady state optimal control problem, but the same dynamic problem with a constant control in the boundary. And this was important to see for us, because this is the same for the time-varying feedback control. For the time-varying feedback control, it also was not a priori clear for us what is the corresponding Turnpike, because it was not the steady state. And considering this, or simulating these optimal control problems, we saw that this is the same for the time-varying feedback control. So the corresponding steady state is also if we just replace the u of t here by some constant u. Then we thought, okay, maybe we can just use the proof that we did before also for this time-varying feedback control, because we can also write down a solution for the transport equation with the feedback control u of t times the final state, times the state at the end of the interval, but this just does not work. And this does not work because we have some nonlinearity in the control here in the solution by the product given by the product, so it is not clear for us yet how to compute the derivative. So this is the current state of the art where we are. So what we're currently analyzing to get an idea of this nonlinearity is considering a transport equation with nonlinear right-hand side, just to get an idea how this nonlinearity works maybe in the proof, how we can handle this nonlinearity in the proof. And then, as I said, this is ongoing work. We hope we can handle the time-varying feedback control problem in the very end. So this is the current state of the art in the Turnpike for the transport equation optimal control under uncertainty. And with this, I want to thank you for your attention.
Thank you very much. Maybe I can start with a couple of questions. From a numerical point of view, how this uncertainty may affect the convergence rate when you solve the optimal control problem?
How the numerics, sorry, can you repeat, please?
If you consider uncertainty,
yes.
How this uncertainty in its distribution can affect the convergence rate when you actually solve numerically the optimal control problem?
For me, this was interesting to see, because I thought I would just need to compute the expected value and do the same computation for the expected value. So just solve the problem maybe 100 times instead of one time. But this was not an increase of time by 100, this was an enormous increase of time. So this is why I only showed like 25 scenarios. The computation was quite hard at this point, even if we just consider the expected value as the average over all scenarios.
Okay. And when you prove this optimal result, there are two constants, one for the deterministic case and one for the case with uncertainty. Do you have ideas on how these constants relate to each other?
Yes, so I can show this slide with the proof again. This was here. So in the end, I have like a quadratic expression in the L2 norm, and using the formula for the quadratic equations, I can explicitly write down the solution here, and the constants appear with some other factors. The constants are defined in the proof, so I can just put the proofs next to each other and see, okay, the constants are slightly different in this point, but they are similar.
Okay. But is the distribution visible in this other constant or
I did
not?
Explicitly compute the value of this constant, because this depends on the epsilon of the strong convexity property and on the Lipschitz constant, which is not a priori given. I just have a function that is Lipschitz constant. So I did not explicitly compute them, but I mean, of course, just putting the constants next to each other, you will see the differences.
Okay. Okay. Thank you. Are there other questions? Yes, please.
What you did was in one space dimension, right?
Yes.
Is there any chance of getting to higher space dimensions?
I can imagine. I mean, in higher space dimensions, like consider three-dimensional flow or something, I can still write down the solution of the transport equation, if I'm not mistaken. And if I still can write down the solution, I would expect that I can, at least in the deterministic case, do exactly the same. The question would be how, if I consider uncertainty, for example, in the source term, how the source term will affect, like, in the different dimensions. But
you can write down the solution that explicit for transportation.
I mean, you can do it for the wave equation, can't you? I mean, we've not really thought about these higher dimensions, because usually when we consider like a pipeline or a street traffic flow or something, the ratio is like 10-kilometer road, but just small road. So the the relation between the dimension is like one dimension is over all. So this is why we only consider one-dimensional problems. So the more interesting case for us would be consider, for example, a system of equations, which would be also kind of extension that we're thinking about, but then we cannot write down the explicit solution anymore.
Okay, yes, please.
I like the result particularly with the variation, where you also presented the confidence interval in the end. So this confidence interval is independent of the capital T, or?
Yes, because this is the confidence.
Important point.
Yeah, because this is the confidence interval of the expected steady state. So there is some, I don't know, delta larger than or equal to 0, such that 80% of the time-dependent scenarios are in R delta minus delta and R sigma plus delta of the steady state. So this is a time-independent confidence interval, and then if the time horizon goes to infinity, like 80% of the dynamical scenarios will be in this confidence interval of the steady states.
Okay, yes, please. No, sorry, Martin. Yeah, you can go.
Thank you for the nice talk. I wonder if, have you ever tried this for the wave equation, for instance? I mean, you can think in this given variable that you can write like the wave operator as a two-transfer operator.
Yes. No, we have not tried yet, but at least for one-dimensional wave equation, I can write down a solution, so I would expect the same results.
And also, like, you have this explicit solution for the other formula for wave, right?
Exactly, yes. So I would expect more or less the same results, different constants, but the proof should be possible to apply in the same manner.
Okay. There was another question. I guess I will do exercise today.
Do you think that like these results can be extended also to take into account uncertainty on the dynamics? So like you have a parameter on the vector field that is distributed according to some distribution. And
Yeah, that is a good question. I mean, I'm not sure if I understood the question correctly, but I would, if I understood it correctly, then this would result in solving stochastic PDEs or something, and not like deterministic PDEs with random parameters. And maybe then the analysis will be different. So I'm not an expert in these stochastic PDEs or stochastic ODEs, and I'm not so sure what already exists for the hyperbolic stochastic PDEs. I guess there is much more work on parabolic or elliptic PDEs. So I'm not sure if I can answer this correctly. I'm sorry.
Are there other questions? Okay. No, sorry. Sorry, we have to let everybody listen to questions. Okay.
Thank you. Just in the proof, you used an explicit formula for the solution, but if there are some chance to prove general proof without using the explicit expression.
Yes.
For instance, when you have diffusion with small coefficient.
I think this is possible. I mean, yes, this is possible by, for example, when you consider, for example, a system of two transport equations, then you cannot get an explicit solution, but you can get like the operator that maps initial and boundary condition to some terminal state, and you can define the adjoint operator. You can get some estimates on the solution by the distance between the control to state operator and the adjoint operator. Then this is possible to also get some Turnpike estimate of this form for a problem in which the solution is not explicitly given.
Okay. I think we can thank you again and pass to the second speaker.